Welcome you all to Sadvidya Academy Science Classes by Ganesh Hebbar. So today's topic is Class 10 Physics Chapter number 12 Electricity Part 5. In this Part 5 we are going to discuss about the combination of resistors. But before going ahead with the system of resistors, we have to know the direction of current. So that is called as the conventional current direction. We have to know the meaning of what is conventional current direction. So in order to explain this, I will draw a circuit diagram. So let us assume that this is a battery. Like this battery is represented with a bigger line and with a smaller line like this, and towards one end there is an ammeter to measure the current, and there is some resistor here like this. So across the resistor a voltmeter needs to be connected, and resistor is named as R, and this is named as, this is positive and this is negative, this is positive and negative. So there is some rule for representing this positive and negative. Wherever you connect the positive of the battery, there you have to connect the positive of the voltmeter as well as the ammeter. So towards the negative side you need to, this is, let us assume that that is the key, and this is, let us assume that this is a general circuit, this is K key and this is the battery, and in battery this side is positive, and this actually it is not a battery, it is a cell, single cell. So now towards the positive side of the battery you need to connect positive of the ammeter as well as the positive of the voltmeter. Similarly, towards the negative of the battery you have connected negative of the voltmeter as well as the negative of the ammeter. So now let us assume this particular circuit diagram. Now tell me in which direction the current flows. So in order to find the direction of current, you have to know what is current means. At this particular point of time, we know that current is the flow of charges, but in specific the charges are electrons here. So it is the flow of electrons. So in a battery, where will be the positive, and this is positive and this is negative, where will be electrons? Electrons will be more towards the negative side and electrons will be less towards the positive side. So anything which is at the higher potential, that it moves to the lower potential always. Say even if it is water, say for example it flows from a higher level to a lower level. Similarly here the electrons are more towards the negative of the battery and electrons are less towards the positive of the battery. So the electrons move from a region of this negative side to a region of positive side. Actually the direction of the movement of electrons is this way, as I have indicated by the arrow marks, like this. Like this the electron should flow in the circuit. But while this concept of electricity was found, so I have given that explanation. The current in any circuit is due to the flow of electrons, we already know. But during the time the electricity was discovered, the electrons were not discovered then. At that time, when the electricity was discovered, they were not knowing about the electrons. That is why they were unaware about the fact that the current is due to the flow of electrons. What they have thought is, they thought that the current, electric current, was due to the flow of positively charged particles. So what they have taken, that is, the positively charged particles will be more towards the positive side. So they have taken the direction of current from positive of the battery to the negative of the battery. Like this they have taken. this is the direction of the positively charged particle. That itself they have taken as the direction of current. But now we know that the current is due to the flow of electrons. But even after knowing the direction of electrons, flow of electrons, we have not changed the direction of current. We are using it as a convention that they have followed it, we are also following it. So internationally accepted convention, that is the direction, conventional current direction. That is why we call it as the, not the direction of current, we call it as the conventional current direction. They may sometimes ask you that what is the direction of flow of electrons. So direction of flow of electrons, direction of flow of electrons will always be, electrons will be always opposite to the direction of conventional current, or opposite to conventional direction of current. That means actually the electrons are flowing from the negative of the battery to the positive of the battery, but we have taken the convention as the current direction is from positive of the battery to the negative of the battery. This direction of current, that is from positive to negative of the battery, is called as conventional current direction. Now we shall move on to the concept of resistance of a system of resistors, or it is also called as the combination of resistors. So there are two methods of connecting the resistor. Say for example, if two resistors are given to me, one is this resistor and one more is this resistor, then I can connect one resistor here and the other resistor here, like that. So one end of one resistor is connected to the other end of the other resistor. That means back to back. If the resistors are connected back to back, then it is called a series combination. And there is one more method. I can connect the two resistors like this. The left ends are connected together. Left or right ends are connected together, and the right ends are all connected together here. Then they are connected like this parallelly in the circuit. Then such resistor combination is called as parallel combination. You will get to know about in detail in the next as we go to learn about that particular series and parallel combination. Let us see what is that. First thing is resistance in series. What is resistance in series? This is the circuit diagram of the resistors connected in series. Here you can look at, I hope the diagram is clear to you. So here this is nothing but a battery, a group of cells, and this is the ammeter which is connected here. Ammeter is a device which measures the current flowing in the circuit, and these are the three resistors R1, R2 and R3. R1, R2 and R3. These are the three resistors. This is R1, this is R2 and this is R3. They are connected. If you look at it carefully, they are connected back to back. The left end of R1 and the right end of R1 is connected to the left end of R2. Similar manner, right end of R2 is connected to the left end of R3. Like that they are connected back to back. Then voltmeter is connected across all the three resistors, and it is connected to the external circuit like this. So this particular combination, that is connecting all the resistors back to back, one after the other, it is called a series combination. So what happens? What is the effective resistance? What is the effect of connecting these three resistors in series? What happens to the net resistance? If we know the individual resistances R1, R2 and R3, but we don't know what is the net resistance in that particular resistor. That is why we are going to calculate the effective resistance in the series combination. Now, in order to find out what is effective resistance in the series combination, we make use of the Ohm's law only. Ohm's law, which we have discussed already. So, according to that Ohm's law, what does it say is V is equal to IR. So, before applying the Ohm's law, what we do is we see, we just alter the positions of ammeter and voltmeter for different trials. First, what we do is we connect the circuit like this, we switch on the key and find out what is V and what is V and what is I. That is V is equal to, we already know V is equal to IR. We already know V equal to IR. So now here in this particular case, V is nothing but the net potential difference which is given, and I is the net current flowing through the circuit here. Here is the current flowing, that is I is the current flowing through the circuit, and R is nothing but the effective resistance in the series combination. So that is called as RS. That means effective resistance in series. That S indicates it is in series. Effective resistance in the series combination. Now, what is done is, in order to find out the effect, once what I do is, in place of connecting the ammeter, what I do is I change the position of the ammeter. In place of connecting this ammeter here, I disconnect the ammeter from here. That I will do direct here, and I will place the ammeter like this. Here is the ammeter in between R1 and R2, and see what is the current flowing through the circuit. So interestingly, I will get the current is same as that of the previous value when it was connected here. In a series combination, when it was connected here, whatever the value of current it was flowing through this particular circuit, the same current is flowing when I connect the ammeter here by connecting it direct here and placing the ammeter in between R1 and R2. I get same value of I. Similarly, what I do, I again remove the ammeter from here and connect it here directly, and what I do is I move the ammeter in between R2 and R3. I place the ammeter here again. At that time also, I note down the current and I will get the same value of current everywhere. Whenever the ammeter was here in the main circuit and in between R1 and R2, as well as in between R2 and R3, the value of current was same. It was we got the value of current same. That is one observation. And one more, so we got the value of current. That means what we can conclude is, then even if I keep that ammeter here also I will get the value of current, that is I only. Whatever the value of current which I was obtaining here, the same current was flowing everywhere. That I can say. Then now what I do is I keep the ammeter here itself. So what I do is I keep the ammeter here only as in the initial stage, but I now change the voltmeter. In place of connecting it here, what I do is, initially I have measured the voltage here. So that voltage was V. So that voltage, when it was connected at the point X and at the point Y, so I got the value of V. Now, when I say I didn't change the value of the terminal of X, what I do is I remove the connection of the negative terminal of the voltmeter at Y, and I will move that negative terminal somewhere here like this. So I delete this. Say I won't connect it here. At that time I see whatever which is the value I am getting. It is nothing but the initially whatever the value of voltage I was getting is the potential difference across the points X and Y. That means across the series combination of resistors. Now, whatever the value of voltage I am getting is across only R1. Am I right? So when I connect this Y terminal here, somewhere here, if I connect, then whatever the value of the V that I get in the voltmeter, it is the potential difference across the resistor R1. Am I right? So that I note down. So but interestingly, I won't get that R1 which is equal to the previous value which is measured across all the three resistors. So I will take that value as V1 because it is of R1. That is why it is a resistance, it is a potential difference across R1. That is why I will take it as V1. Similarly, what I do now is I connect this voltmeter in between this terminal like this as well as like this. For the first trial I am connecting only to R1. For the second trial I am connecting it only this. I have disconnected here and connected it like this here. That means now the voltmeter is only to R2. Now also I am getting some other value of V2 which is not equal to V1 or not equal to V. So when I place the voltmeter across R2, I will get a value equal to V2. That value I will note down as V2. And interestingly, the third point, third trial which I do is I keep the Y point fixed, I remove the X point from here and I keep the voltmeter only to R3. That means now I am measuring the potential difference or voltage across the resistor R3. So I will get a different value of R, that is when it is placed across R3, the value of potential which I am getting, I note it as V3. And the main important observation I can make by looking at V1, V2 and V3 and the actual value of V which was present, if you look at that values experimentally, I observe that this V main potential difference when it is placed between the combination is equal to the sum of the potential differences across R1, that is V1, plus the potential difference across R2, that is V2, and the third one is the potential difference across R3, that is V3. So this value I will obtain. That means finally I end up getting what? The main potential difference V across the combination is equal to the sum of the potential difference between the individual resistors. ಅನ್ನೋ ಕಾನ್ಸೆಪ್ಟ್ ಸಿಗುತ್ತೆ. Now apply Ohm's law for each of the terms. So but we know that V is equal to, we already have written V is equal to I into Rs. And V1, how to write V1? So I have said that I is always remaining a constant in series. You have changed the ammeter position but the current has not changed. So for all the values I will keep the value of I is same. I into, but the resistance value is different, IR1, like that V2 equal to I into R2, like that V3 equal to I into R3. So substitute all these values in these equations. At that time whatever I get is V, that is I into Rs, is equal to I into R1 plus I into R2 plus I into R3, or I is common here so that I can take I into R1 plus R2 plus R3, which is equal to I R S. So I is common because I is common in all the three terms. That is why I have taken it outside, and R1 plus R2 plus R3. Now I and I gets cancelled. So what is remaining finally? Rs. Effective resistance of the series combination is equal to R1 plus R2 plus R3. That means effective resistance of the resistors in the series combination is equal to the sum of the resistances or sum of the individual resistors. This is a very important formula in your for your examination point of view as well as problem solving point of view. So I can say that the resistance or the effective resistance of the system of resistors connected in series is equal to the sum of the individual resistors, that is Rs is equal to R1 plus R2 plus R3. Next we shall move on to one more combination of resistors, that is system of resistors, that is called as parallel combination of resistors. How does the circuit diagram look like in parallel? That is resistance in parallel. This is nothing but the circuit diagram showing the resistors which are connected in parallel. If you look at the circuit diagram more clearly, you can see that these R1, R2 and R3 are the three resistors which are connected. The left ends of all the R1, R2 and R3 left ends are all joined together. At the same time, all the right ends of all the resistors are connected together and then they are connected to the circuit. That means they are not back to back. Left ends are all connected together and right ends are all connected together and then they are connected in circuit. Such a combination of resistors is called as the parallel combination of resistors. Now here what happens to the effective resistance in the combination of resistors, that we are going to discuss. So we already have found the effective resistance in series combination, that is Rs equal to R1 plus R2 plus R3. Similarly, whatever the value of Rp, that is effective resistance of the parallel combination we will get, that we need to find out here. So in order for that, what we do is, so we perform this experiment. So we know that while performing the experiment we will get, when I switch on the key, I will get some readings in the ammeter. Similarly, I will get some readings in the voltmeter. That is actually the V is equal to, that formula for V is equal to I into R. That means here V is equal to, so V is equal to I into R is the formula from Ohm's law. Now, or else I can rearrange this equation as I is equal to V by R. I is equal to V by R. V is equal to IR or I equal to V by R. In that manner also I can write. Now, what is the thing is, so first what I do, here R is nothing but the Rp, the effective resistance of the parallel combination, PR subscript P. Is that clear? So now what I do is, similar as in the previous case, what I do, so I remove the ammeter from here. So remove the ammeter, I will connect it directly. When I remove the ammeter, there will be direct circuit like this. So, and I place, in different trials, I place the ammeter. Once I will place it here, that is ammeter, I will place it here and switch on the circuit and measure the value of current. Let us assume that here the current was I. When I was when I have connected the ammeter here, it was I. So when I connect it at this particular point in the main circuit, so that we call it as the main current. So main current was I. Now when I connect the ammeter at along with the R3, let us suppose it is R3, so not R1, it is R3. Now when I connect it with the R3, I will get some value which is not equal to the main current. So I have connected to R3, that is why the current that is flowing through R3, that I will take it as I3. So the current flowing through R3, current through current through R3 is taken as I3. Similarly, what I do, I remove the ammeter from here. Again, I connect it across R2. Here I will connect the ammeter. At that time, what happens? So, the current that at that time also, I will get some different value of current which is not equal to either I3 or I. So, I will get some different values. Current through R2, that I will take it as I2. Similarly, I remove the ammeter from here and connect it along I1, along the R1 resistor. So at that time, whatever the value current through R1, the same is the, if I measure the current here, same current will flow through R1, right? That is why I have written current through R1, current through R2 and current through R3. That means when I measure the ammeter reading here, it is nothing but the current which is flowing through R2. I hope. Like that, when I connect it at I1, it is the current flowing through R1. Similarly, when I connect it through R3, it is the current flowing through R1, R3. So that is why I will get different values of current. But one thing is, one important observation you can make is this I1, I2, I3, if you add them up, the currents, if you add them up, I1 plus I2 plus I3, if you add them up, interestingly you will get a value which is equal to the main current which was flowing when the ammeter was connected here. It is an interesting fact, that is I equal to I1 plus I2 plus I3. And one more thing is, what I do now, I have changed the ammeter from one point to other point. Similarly, now it's the time to change the voltmeter position. So what I do is, from this position, whatever the value of voltage we have got is, that I will retake it as V, that is the main voltage. Now I remove this, no need to remove this. From general knowledge we can say that if I, in place of I have connected it across these 2 points, that means I have connected it across R1 as well as I have connected it to across R2 as well as I have connected it through R. That means even if I change this position from here to here or here to here or here to here, the values will not differ. They will be same. I hope. I hope you understood. So the value of voltage remains the same. Voltage or the potential difference remains same. So remember, in the case of a parallel combination, what happens? Voltage remains same, but the current changes from one branch to the other branch. But it is the opposite case in the case of series combination. In series combination, current remains same, voltage gets divided. So now apply the Ohm's law here. So I is nothing but V by RP. We have already written. So V by RP equal to I1. I1 is nothing but V is same. So I is equal to V by, I can write it as R1. Similarly, that is I1. So similarly, I2 equal to V by R2. Similarly, I3 is equal to V by R3. Substituting all these values in this expression, what I will get is V by Rp equal to V by R1 plus V by R2 plus V by R3. This is R2. So V is common everywhere. This is not 1, this is V. Okay, so V is common everywhere, so it gets cancelled. So what is remaining? So that is 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3. This is the formula for the effective resistance of the system of resistors when the resistors are connected in parallel. What is the meaning of that? That means always remember it is not Rp equal to, you are not directly getting the value of Rp, that is effective resistance of parallel. You are getting the reciprocal of the effective resistance in the parallel combination is equal to the sum of the reciprocals of the individual resistors. That you have to remember. So it is not Rp equal to R1 plus R2 plus R3. No. So it is the reciprocal of the effective resistance in parallel combination is equal to, it is not the sum of the resistors, it is equal to the sum of the reciprocals of the individual resistors. That is about the parallel combination or the effective resistance of the parallel combination. Next question is how to obtain maximum and minimum effective resistance. If we want to get out of the three resistors, we want to get a very large resistance. How we need to connect? In the similarly, if we want to get a minimum resistance out of the three resistors, how to obtain? The answer is direct. That is, we obtain maximum resistance by connecting resistors in series. Why? Because the formula of the series combination of resistors itself says that the Rs is equal to R1 plus R2 plus R3. That is, the resistors gets added up in a series combination. Similarly, in order to get a minimum resistance, how we need to connect? We obtain minimum resistance by connecting the resistors in parallel. Why? Because the formula itself 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3 it is. That is why when it is the reciprocal, we will obtain a minimum resistance. Now, what if here we have taken three resistors? What if there are n number of resistors in series? If number of resistors is in, say for example, n numbers, so then the formula is simple. So that is Rs is equal to R1 plus R2 plus R3. Like that, how many times? Like that you have to go on adding up to Rn. That is the formula of series combination. Similarly, in the case of parallel, 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3. Like that, go on adding up to 1 by Rn. This is the formula of effective resistance when n number of resistors are connected. Say for example, if there are only two, then if two resistors are connected, then the formula becomes very simple. That is Rs is equal to R1 plus R2, but Rp equal to 1 by Rp is equal to 1 by R1 plus 1 by R2. This you can actually simplify. That is R1 plus R2, R1 plus R2 divided by R1 R2, but it is 1 by Rp towards left side. So Rp is equal to R1 R2, reciprocal of this. So R1 R2 divided by R1 plus R2 if there are two resistors. This is one formula, and if there are two resistors, series combination is this particular formula. Let us sum up the concepts we have discussed in this particular part of this chapter. First concept we have discussed is meaning of conventional current direction. Next, effective resistance in series combination. Next, effective resistance of parallel combination. And the last one we have discussed in this part is methods of obtaining maximum and minimum resistance in a circuit. That's all we have studied in this particular part 5 of this particular chapter. Thank you.